livestock emissions continue to be the elephant in the room when it comes to limiting warming over the coming decades. It's well known that grazing animals such as cattle, sheep and goats are one of the largest sources of methane. It's also well known that methane is produced in the stomachs of these animals known as ruminants. Methane is a natural byproduct that comes from the process of digesting grass and other fibrous foods. It's known that reducing methane is the single most effective strategy to reduce global warming and its impacts in the near term. Yet despite these simple well-known facts, the solution is far more complex. Even though we live in an increasingly urbanised world, livestock is still deeply ingrained in our cultures and societies. These animals provide a staple source of food for the majority of the world's population, where they're a major source of highly nutritious protein. Where and how people purchase and consume dairy products and meat varies across cultures, though the sources of these foods are the same. Over 1 billion people are reliant on cattle and sheep for their livelihoods. But the roles cattle and sheep play in many societies go far beyond food. Livestock provide vital functions including draft power, transport, and these animals play critical roles in many religious and cultural traditions. Methane is a small molecule gas that traps heat in the atmosphere, leading to warming. Most methane comes from life. This is mainly from microbes called methanogens. These are found in the stomachs of cows, as well as where plant matter decays, such as in rice paddies, wetlands and landfills. Methane is a short-lived greenhouse gas, as it's broken down quickly to carbon dioxide in the atmosphere, usually in around a decade. Enteric methane is methane resulting from the microbial activity in cows' stomachs that digest grass and other plant materials.
Since the warming from methane comes from the last 12 years of emissions and not from historical emissions necessarily, that warming comes from the latest 12 years of emissions, and that's 80% from non-OECD countries. So therefore, the methane challenge is probably the most intimately linked mitigation and development challenge.
I have seen just in the last 3 COPs that I've attended, it went through how would we grow food in a changing climate to can we grow food in a changing climate. That's how urgent this is. You cannot think about what's happening in the world without understanding that the vast majority of the world's farmers are very small scale subsistence farmers.
Where Ethiopia, Kenya, part of Uganda is also Djibouti, that area. We lost almost 10 million heads of cattle to drought. And this was a 6th failed season of rains.
There is large agreement, I would say, that methane is a different beast compared to other environmental pollutants, such as nitrates or ammonia or other gases and compounds. Why is it different? Because methane, in contrast to the other greenhouse gases, is very short-lived. It's not just produced by sources such as cows or rice paddies or landfills, but it's also naturally destroyed and has a short lifespan as a result.
It is destroyed primarily in the atmosphere by nature's detergents, radicals like chlorine and hydroxyl or OH. These are the compounds that sort of cleanse our atmosphere in general. And they break methane down on average in about a decade. And that's compared to, centuries or thousands of years for carbon dioxide and a century or more for nitrous oxide, the other greenhouse gas. And that combination of potency and short lifetime is why action on methane is so important. If we could eliminate all methane emissions from human activities, a big if, we could restore methane's concentration to pre-industrial levels in only a decade or two. And we'd save half a degree C of warming if we could do that. And we could see that in my lifetime and yours. there's nothing else that gives us this much power to slow global warming over the next decade or two.
Methane is produced by the microbes in the animal's stomach when they digest fibrous plant materials. This digestive process is the same for both domestic and wild ruminants. The fact that individual animal methane emissions vary greatly provides a huge opportunity for reduction.
In the ruminomics study, we had cows that would emit 100 grams of methane per day, and we had 500 grams per day from a different cow in the same herd. So it's 5 times more within the same herd. So you can reduce
on
it
the same
5
diet
times.
and the same everything else.
Exactly.
The data that we've collected thus far, we've had about 900 animal records in the last 12 months, individual animals of methane emissions. We see a wide divergence within populations that are quite similar genetically, right? All the same breed, fed the exact same diet, and we can see variations 30+% between individual animals that have similar performance. So that's a huge variation, right?
This variation in emissions that exists across animals provides a real opportunity to reduce methane output from livestock systems.
We'll be working very much on the genetics of animals, estimated breeding values, improving those, getting good EBVs for methane efficiency.
Past research has shown there is a heritable component of methane, right? So there's something about the host, there's something about the microbiome, and there's something about the interaction that drives these differences in methane emissions we observe.
Respiration chambers, such as these new systems at Cornell University in upstate New York, are a critical step in better understanding methane emissions and how they can be reduced. While in the chambers, the amount of feed each animal eats and milk production are monitored, as are methane, carbon dioxide, oxygen, and hydrogen levels.
These are basically standalone units that allow for the measure of gas, basically gas exchange. And so that's the measurement of carbon dioxide, methane, nitrous oxide, hydrogen, and that's being emitted from the cow, but also measuring oxygen consumption, which when combined with the CO2 that's being exhaled, you can estimate heat production. And that's really important knowledge to have to better define energetic efficiency in dairy cows.
At this time, the emissions from the cow in Chamber 3 is over 140 parts per million. While for the cow in Chamber 1, it's around 225 parts per million, an increase of over 50%. Yet these animals are fed an identical ration and are similar in size, so should have the same emissions based on the current predictive models. This further confirms the work of Itzik Mizrahi, Sarah Place and others around the yet to be understood causes of this significant variation and the need for greater levels of monitoring.
Are these animals always low and high methane emitting? Or if you change the diet, does that shift? And those things haven't really been done because we don't really look at that sort of thing. So we need a lot more money. And I think we need to be able to work in a lot of countries where there are large numbers of cattle. And so that are, like India and Brazil, those are where most of the animals are. Most of those in extensive systems. And so we need to think seriously about how to deploy these technologies and have really technologies that are relevant and applicable to those sorts of systems.
When it comes to things like enteric methane, we don't quite have all the solutions at hand to make the large impact that we know we need, especially for operation grazing systems, pasture-based systems. But we're starting to see the emergence of tools and really driving the adoption of that. And again, putting the capital where it's needed at the stage of development. Right, we're in innovation phase right now. We're trying to develop innovation. We're trying to understand the space better. We're trying to get better measurements from these animals. That's where we need it. And unless we can recognize the nuance within each sector, we're not going to make the impact we need.
we'll also be working on measurement and validation systems, and that is one of the big things that's missing in this whole environment, is accurately quantifying what is actually going on.
Measurement is a big challenge in the livestock sector in terms of understanding what a specific solution does in terms of reducing methane. And we need to be able to rapidly, cheaply assess what that is, what kind of emissions are coming from different solutions that are being put on the table.
As much as reducing methane is urgent, a holistic approach is vital to ensure food production is not compromised.
Focus has been really on one variable most often, like looking at methane. And so what we don't want is, we don't want solutions that inhibit methane, which solves one problem, but creates a different problem. Like, we want to maintain nutrient digestibility. We want to reduce nitrogen sort of excretion. We want to maintain efficiency.
Measuring emissions from the thousands and thousands of animals required for breeding for lower emissions will not be possible through the use of chambers. They're expensive, immobile, and require animals to be trained to use them. Alternative, affordable, mobile and accurate monitoring systems are urgently required.
So we need to collect a boatload of phenotypes, right? Thousands and thousands of animals, meaning we have to actually measure methane emissions from thousands of individuals to get a better understanding of those inherent, right, opportunities for genetic selection.
To help address this, Cornell is working with livestock technology startups AgSen and Optiway to validate their system against the respiration chambers and provide data to improve their algorithms. Self-contained solar-powered mobile methane and live weight monitoring systems like the AgSen Optiway can be used in the environments where cattle are produced, enabling farmers and ranchers across the developed and developing world to better understand and manage their emissions. A salt lick is provided to attract the animal, and emissions and live weight are monitored each time an animal comes into the sensor unit.
The demand for food in general is increasing, and in particular for livestock products in low-income countries is increasing as well. And so how do we do this? How do we meet this the challenge in a sustainable way, so that we make sure that we take care of the environment, we take care of the planetary health, at the same time try to meet the demands and the needs of people as well.
One of the exciting projects that we're working on right now is if a certain type of seaweed can actually reduce methane emissions.
But then when we go into rural areas, the animal products and the animals are just very important, especially ruminants, because they can convert what we cannot eat, like pasture, grasslands, to milk, and also crop byproducts. So with crop byproducts, and Sue will maybe also argue with me, maybe we want to put that in the soil because we can also use that for composting and so on, but we can also use it to feed to the animals, and they produce something for us. Especially if a dairy animal in a rural area, it's going to give you protein every day, and which is very important for just nutrition.
While people say, yeah, okay, cattle have always produced methane, ruminants have always produced methane, and wild ruminants will always continue to produce methane. It's something which is within our control. We can actually influence that. And if it reduces climate impact, why would we not want to do it?
You know, ultimately, reducing methane, if you haven't got a production value, is all about who pays. Because someone has to pay ultimately.
Having said that, the producers will always say, yeah, but who's going to pay for it? That's the big question at the moment.
I mean, I saw one interview with a French farmer who was complaining simultaneously about the risks coming from climate change and also the regulations that are being forced upon him, as he saw it, to deal with climate change. And of course, that squeeze is effectively a squeeze that is created by our expectations of the markets.
Is it at all possible to set up a system that those who benefit compensate those who bear the cost? Because, you know, as an economist, I think that's the gold standard for determining the optimal level of any natural resource use that's both an asset and a liability, like wildlife is an asset and a liability. Some people want more, some people want less. Those who want more, should pay for it, and those who bear the cost should be compensated in some way.
Livestock methane has become increasingly politically divisive.
This is not about not eating meat. This is not about necessarily reducing cow herd sizes. The way that we want to approach it this decade is to improve productivity while we're developing the new technologies that can reduce emissions in absolute terms.
So the biggest barrier is having solutions to adopt, and that means we need a market signal. We need some sort of signal for innovators in the space to develop technologies and solutions that will work in those specific systems. Otherwise, we'll continue to get iterative development, and we won't develop the solutions in time to where we need them.
We talk a lot about the yes and approach, and that's really recognizing that we need a multitude of solutions. The food system is incredibly diverse. There's unlikely to be any silver bullet to bringing about sustainability in the food system. And so we need 1,000 flowers to bloom, and sometimes they can be kind of seen as opposite each other, right? So in the area of livestock, we talk about needing livestock to be sustainable. We can find all sorts of ways of reducing methane. We can reduce the land footprint of our animal source foods that we're producing. And we need to look at alternatives to that. And that could be coming from alternative proteins or even cultivated meat. In a world with 10 billion people, with such diversity of production systems, of climates, of cultures, of contexts, of tastes, of religions, what we need is diversity, and we need to value that diversity. And there could be multiple ways of delivering a sustainable food system.
A lot of it isn't rocket science. It isn't that we don't know how to do it. It's that we haven't figured out yet how to enable farmers or incentivize farmers or the food companies or, all along the supply chain to actually make that change. And so that's where we're focusing on.
Methane funding falls well short of the potential opportunity for limiting warming.
Less than 5% of climate finance is addressed toward methane, and less than 2% of that finance is on the livestock sector. So there is a lot to do to make sure that livestock and also methane issues deserve enough funding.
Production systems have intensity factors of emissions per unit of milk or meat that are probably threefold, fourfold of what we could be achieving, really. And so I think, development finance and funding development finance to make that shift is going to be really important.
We need to be thinking about stacking technologies into an overall farm system. There will not be a silver bullet. There will not be one widget. There will not be a single policy that will go towards how we solve emissions from agriculture. It's going to be the story that developing best practice in agriculture has always been, which is incremental, lots of things stacked together to build better systems.
We need to be looking at everything from genetics and selecting cattle. We need to be looking at what cattle are eating, and that's everything from kind of food, feed, and inhibitors and things like that, but also just good feed. And we also need to be looking at kind of more moonshot opportunities that we might have. We're interested in, for example, the vaccine for methane.
We need to have a strategy that makes sense in the context of different regions and different socioeconomic strata.
Most of the research in emissions has been in the global north. There's very little capacity on the African continent. And that's what we're trying to build with our laboratory at ILRI. And we try to capacitate more people on the topic. And Bernard is working on emissions as well and on the inventories to understand that better.
Most of the countries don't have access to tools to measure methane, especially if developing countries are contributing almost 8% of the total methane emissions. Of course, we need to accurately measure those ones because it's really a big hotspot.
We need to knuckle down as Africans and say, guys, what are our comparative advantages here from genetics, from knowledge, from the fact that we've got so many youth, and we've got so many aged farmers are now being looked at as being, a problem. They are a wealth of knowledge. They are the people that have fed Africa's billion to date.
If we utilize the technologies that we've been developing for genetics so far, embryo transfer, artificial insemination, these combined with our knowledge of low methane phenotypes, we can really drive these genetics forward. Using the same technologies that we have today, all we need is the data. And what's beautiful about that is not only do the emissions reductions compound year after year, but they're more or less permanent.
In Africa, we have land, we have natural resources, including water. What we don't have is technology, and that's where we need to focus more. We need to do much more on adoption of technologies, accessibility of technologies, affordability of technologies for those countries. And in Asia, it's a different story because Asia has less resources now.
With sufficient investment and the right technologies, mitigating enteric methane is possible. Acting now will limit warming in our lifetimes, providing opportunities for future generations to avert the worst climate change scenarios.